Welcome to the second class of the biomolecules. In today's class, I'll be talking about the proteins, which is the part two of the proteins, so whatever I have left from yesterday, and also about the carbohydrates, the basics of carbohydrates. So first of all, I want to give basics of the chemical bonds. So there are different kinds of bonds, right? So first is covalent interactions. So what is covalent interactions? Can anybody say, can anybody remember anything? Anybody remembers anything? Is covalent bond? I'll give options. Is covalent bond the sharing of bond? Sharing of electrons, or it is giving of electrons, or it is accepting of electrons, or is it just an attractive force between electropositive and an electronegative atom? Or is it just a hydrophobic interaction? What is covalent bond? Okay, let me give this also A, B, C, D. So what does covalent bond say? Which option is covalent bond? Yeah, I got an answer.
Sharing of electrons.
Yes, Aryaman, you are right. Sharing of electrons is covalent interaction. What do we call giving of an electron or accepting an electron?
Ionic bond.
Yes. So who is this talking?
Vamshi.
Excuse me.
Vamshi, ma'am.
Okay, correct, Vamshi. What is it called? Come again.
Ionic bond.
Yeah. What do we term as the attractive force between an electropositive and an electronegative atom? If
Electrostatic.
electrostatic. Okay, let me put it. I'll extend this question. Like you already have a molecule, for example, water, like OH. OH. This is slightly electronegative and this is slightly electropositive. This is slightly electropositive. This is slightly electronegative. What happens is these two people will get attracted. What does this called? What is this called? So here, what is this atom?
Hydrogen.
Yes. Hydrogen being attracted to an electronegative atom is called hydrogen bond. This is a weak interaction. Coming to hydrophobic interaction. Hydrophobic, what do you mean by phobia? Phobia is
Fear.
hating. Yes, it's fear. So these, whichever molecule that doesn't like the water are called hydrophobic molecules. How do they react with water? If I keep two molecules, they'll expose themselves least to the water, means they become aggregated. If I keep three molecules like this, like if you have seen the oil will form a droplet so that it comes in less contact with water. Only here you can see the water, right? And if you take the second one, like if another molecule is there that is in the water, the second oil droplet will look like this. But if these two come in contact with each other, these two hydrophobic will come to become one group. They become a single group and they release the water molecules from their surfaces. So in hydrophobic interaction, what happens? Whichever people are not liking water, whoever are have the fear of water, they aggregate together and they form a clump in the water. That is your hydrophobic interactions. So why I'm talking about interactions is today's class will be dealing little bit about other things. That's why. So denaturation of protein. What do you mean by denaturation of protein? Denaturation of protein. What is denaturation of DNA?
Breaking of the protein.
Yes, it's breaking. Can I break primary, secondary, tertiary, and the secondary quaternary structures also? No.
Secondary structure is denatured.
Yes. From who is talking?
I'm
So from the secondary, okay. From the secondary structure, we can break it. So secondary will be broken, tertiary will be broken, and the quaternary will be broken. If anybody remembers, what is the kind of bond that we can see in the primary?
peptide bond.
Yes, good. It's peptide bond. For the secondary, what kind of bonds can be observed?
Hydrogen bond.
Yes. Tertiary, you can observe hydrophobic interactions, which are the major interactions, and you can observe the H bonds also. You can observe ionic interactions. You can observe, what is another one? If anybody remembers. I remember covalent interactions, which is intrachain disulfide bonds. One more I have left. Anybody remembers?
Van der Waals.
Yeah, van der Waals. So the quaternary will have all of these interactions along with interchain disulfide bonds. So to break the protein, you have to break these bonds, right? Any of these things is broken, the structure of the protein is broken, which is clear, right? So let's see what can break the protein. I say that strong acid and strong base can break the protein. Because acid and bases can have protonation, they have the effect of protonation and deprotonation, they can disrupt the hydrogen bond. And the next thing that can break a protein structure is organic solvents. Okay, organic solvents are hydrophobic or hydrophilic? Can they break hydrogen bonds?
Phobic, ma'am. Hydrophobic.
Yes. Can they break hydrogen bonds or not?
Not.
They can break the hydrogen bonds like ethanol, because ethanol has what? OH. Ethanol has OH group and it can break the hydrogen bond. Means they can disrupt with the hydrogen bond. So whichever molecule that you take and that can disrupt the hydrogen bonds, those all can break the proteins. Coming to detergents. Detergents can be ionic or non-ionic. They can disrupt the ionic bonds or salt bridges. Again, your ionic bond is broken. One can break the hydrogen bond, so your protein is the protein gets denatured because of that. One more interesting candidate I have is reducing agents. I'll give an example and somebody has to say where we are using it and why. Beta mercaptoethanol. Ethanol. Beta mercaptoethanol. It's famous for what? Okay, beta mercaptoethanol is used during DNA isolation. Okay, in order to break the disulfide bonds. Why do we have to remove the protein in the DNA isolation? Yeah, correct, Satya. Why do we have to use the beta mercaptoethanol for the DNA extraction? Okay, if we break, like the proteins can interfere with the DNA absorbance. How many of you agree with that? That protein can interfere with the absorbance capacity of the DNA.
Yes, ma'am.
Yes. Because protein also gets absorbed at UV range, like they get detected in the UV range, and DNA also gets detected in the UV range. When extracting DNA, if you have a protein, you will get overestimation. Yesterday we discussed, right, at 280 nanometer, the protein that contains the aromatic amino acid can absorb. In the same way, if we want to estimate a DNA without removing the protein, we'll get the overestimation. And we won't get the pure DNA. That's why we use a reducing agent, beta-mercaptan in order to excuse me. The reducing agents will be used in order to break the protein structure. Then the one more thing I forgot is heavy metal ions. So heavy metal ions can disrupt the ionic bridges or the salt bridges. Again, they can break the interactions or the proteins. I have a question. If a protein is denatured, can we renature it? If a protein is denatured, can we renature it?
Yes.
We have application of it. Yes, we can renature it. And where do we find the application of this? The protein gets denatured and we can renature it. Okay, I'll give a clue. Stress bleeding. Have you heard of molecular chaperones? Molecular chaperones are those proteins that can fold the protein, but they do not get involved in the final structure of the protein. They are not present in the final structure of the protein. The chaperones are like cylindrical structures that can take up the unfolded protein or the protein that has been opened, and they can refold it and send it back as fresh as new, or they can send it back as physiologically active, that it can perform its function again. What is a famous example for molecular chaperones? What is the famous example for molecular chaperones? Heat shock proteins. Have you heard of heat shock proteins? Heat shock proteins, HSP60 and HSP70. These are proteins that are responsible for giving the stress resistance. So heat can destroy the protein structure. Heat can destroy because of the heat, the molecular vibrations will be high. Due to these vibrations, there will be breakage of weak interactions. So heat can destroy the structure of protein. That's where it comes, heat shock proteins. When heat destroys the structure of protein, cell has the inherent mechanism of producing the heat shock proteins, and they will give the stress resistance to the cell. Like they will reform the proteins that are unfolded, and they'll refold it back to its original conformation. Coming to the solubility. A solvent can dissolve the solute in it only if the solvent is able to interact with the solute more than the interaction between the solute molecules. For example, water can dissolve NaCl only if water can react with Na and break it. Otherwise, it can't dissolve it. In the same way, proteins are soluble at only certain conditions. What can affect this? What are the factors that can affect the protein solubility? I have a question. At isoelectric point, when net charge on protein is 0, what about solubility? Will it be high or low?
Low.
Excuse, I couldn't get. Excuse me? What will be the solubility? Yeah, it will be low. It will be low because water is a polar molecule. And at isoelectric pH, you will have the protein molecules coming together and aggregating. They become clumped and it forms the precipitation. That's how pH can affect the solubility of the protein. At a lower pH, I'm talking about a protein that contains just the standard groups. Let's take this protein. Sorry, this amino acid. At a lower pH, what will be the charge on this amino acid? Yesterday we have discussed it, right? What will be the charge on the amino acid at a lower pH?
-1.
At a lower pH, it will be, again, think again. At lower pH, yes, Dipanshi, you are right, +1. Because at lower pH, this will get the H. And this +1 remains like that. So it will be +1. When the charges on the proteins are same, if you take a particular protein molecules, like let's take 3 protein molecules and they have the same charge, they repel from each other and the solubility will be high. So the graph goes like, if you have isoelectric pH here, if this is the pH and if this is the solubility, the graph looks something like this. Behind and after, I mean lower and the higher the isoelectric pH, you will have higher solubilities and least solubility at the isoelectric pH. So when there are ions, what happens is you have protein molecules. So in protein molecules, what happens? No, hydrophobic, already we know that they are in fear with water. So what they'll do is they'll go into the center. In the center, you will get to see non-polar amino acids. In the surface, you will get to see the polar amino acids, polar charged and the polar uncharged amino acids. Remember this point because this will be discussing later also. In the center, you will have non-polar because these doesn't like the water. In the outer surface, you will have polar because they can interact with the water. They are polar. So it increases the solubility. So what happens when I add ion, when you have low ionic concentration, let's say it has plus, plus, and plus, and plus. Plus and plus, maybe here minus, minus, plus. You have some minus. When there are no ions, there is a possibility of interaction between these protein molecules. But when I'm adding ions like Na plus, Cl minus, so let's say I added Cl minus here. So adding ions will reduce the interaction between the solute molecules. What does this do? This will increase the solubility or reduce the solubility. When interaction between the solute molecules is less, the solvent can interact with solute more, right? This can increase the solubility or reduce the solubility. Yes, it increases the solubility. So when we add the salt for up to some point, which is called salting in, we have increased solubility. But after some point, what happens is, because these all salts will come and they'll bind, the hydrophobic groups will get exposed, and these hydrophobic groups will come together and they clump. This will decrease the solubility. This is known as salting out. Coming to the effect of solvent. What happens if we add more of solvents, organic solvents like acetone? Organic solvents have less dielectric constant. So to talk about dielectric constant, it's simple. If a molecule has higher dielectric constant, its solvating ability is more. Water has higher dielectric constant, and that's why it acts as universal solvent. What happens when I add, so let's take water which has higher dielectric constant. If I add a substance of lower dielectric constant, what will be the dielectric constant of the overall solution? Come on, it's simple. It reduces. As overall dielectric constant reduces, the solubility also reduces. That's how solvent will affect this. That's how the different solvents will affect the solubility of a protein. Coming to simple and conjugate proteins. So in conjugated proteins, you will have a simple protein, and also you will have another non-protein component. The non-protein component is called prosthetic group. And the conjugate protein without the prosthetic group, conjugate protein minus the prosthetic group, is called apoprotein. Prosthetic group plus apoprotein is called holoprotein. Give an example of the conjugate protein, if anybody knows. Yes. Dielectric point is, see, if a solution has higher, if you take a solution and it has higher dielectric point, dielectric constant, means its solving ability is more. Water has higher dielectric constant. That's why it can act as universal solvent. What happens is, to the water which has higher dielectric constant, let's say water has dielectric constant of 98, and you add a substance that has a dielectric constant of 67, the overall dielectric constant of the solution is going to reduce. That's why when you add an organic solvent, the solvating ability is going to reduce. That's how the organic solvents can affect the solvating ability. Yeah, the punchy nucleoprotein. Yours, is it clear? Is it fine? Dielectric constant point? Okay, Dipanshi. Okay. So you are saying for conjugated protein, nucleoprotein. Okay. Let's see the example. Let's see whether we can call hemoglobin as a conjugative protein or not. Yeah, chromoprotein, yes. Chromoprotein, yes. Hemoglobin is a conjugated or not? Hemoglobin is a conjugated with the conjugated heme protein. And another example would be metalloproteins. Can anybody say you have read plant physiology? Like, is it being taught or thought, or you people have watched the Agriadics videos? I have questions. I have a match the following. Alcohol dehydrogenase, cytochrome oxidase, immunoglobulin G. Yes, immunoglobulin. Yes. Cytochrome oxidase, nitrogenase. Yeah. So I'll give option zinc and copper and iron, molybdenum and iron. So who will say what is it for alcohol dehydrogenase? What can we match it with?
Zinc, ma'am.
Yes, it is a metalloprotein. So alcohol dehydrogenase contains zinc. Remember, you can get this question. Like they can ask you to match it. Cytochrome oxidase, what can I match it with? Cytochrome oxidase. I can match it with copper and iron. Nitrogenase, as you already know, molybdenum and iron. Where does nitrogenase come? Come on, you people know. Where does nitrogenase come?
Nitrification. Nitrogen.
Yeah, correct. Shreya Chiller. Who talked now?
Kavya.
Okay. So fibrous and globular proteins. The fibrous and globular proteins, fiber, you know, right? It will be rod shaped. Any fiber you take, it will be rod shaped. It will be insoluble and it is tough. Globular, as you know, hemoglobin is a globular protein. So in globular proteins, no, the arrangement that I have explained earlier can be clearly seen. And in case of globular protein, you will be able to see the alpha helix that is longer. And you inside the globular protein, you will have the hydrophobic groups. So what are these amino acids? These are non-polar amino acids. So non-polar amino acids like glycine, alanine, proline, valine, leucine, isoleucine, methionine. Remember, valine is a non-polar amino acid and polar amino acid. In that, remember, glutamate is a polar amino acid. This point we'll be discussing. So amino acids polar like glutamate will come in the surface. And the amino acids like valine, which are non-polar, should come in the inside. That is how the protein structure will be made. This is about globular proteins and the fibrous proteins. Let's discuss about sickle cell anemia. Sickle cell anemia. So sickle cell anemia is caused because of the hemoglobin, right? Hemoglobin structure will be changed. Can anybody say about the replacement of the codon?
Valine.
Yeah. So glutamate will be replacing, valine will be replacing the glutamate. So what happens? When the valine replaces the glutamate, the surface of the hemoglobin becomes hydrophobic. Then the hemoglobins will come and clump together. This will reduce its solubility and make it sickle shaped. That's how sickle cell anemia is caused. And the hemoglobin contains alpha-2 and beta-2 genes. Why I have kept this slide is, if you can see here, you can see multi-gene families here. Alpha-1 and alpha-2 are coded by one gene family. And the beta, these two are on the same chromosome. You are able to see the hemoglobin genes. This is what is multi-gene family at the biochemistry level. This is what they mean by multi-gene family, that the same, those that are encoding for different or the related proteins will be clustered together to form a multi-gene family. And one more thing I wanted to explain is about these codons. So in codons, why do we get synonymous and non-synonymous is because if you can carefully see here the glutamate and the aspartate. So if the third codon gets changed, the synonymous and non-synonymous mutation topic is over, right? I'm not getting any replies. Is that topic over? Okay. So in synonymous mutation, what happens? Even when the fourth codon is changed, it will be changed by the amino acid of similar kind. So you won't see any difference in the structure. Hemoglobin, that sickle cell anemia was a best example for the missense mutation, where the change in the amino acid is going to change the structure, right? Here, if you can see this, even if the fourth one changes, it will be changed to something that is of similar kind, that is negatively charged, aspartate and glutamate. That's why in the codon, if the third base is changed, you are not going to get much difference. Coming to protein sequencing. Protein sequencing, there is no much to tell. Like there is something called N-terminal analysis. This is being introduced by Sanger. This Sanger, and this is given by Sanger. So don't get confused. Even in DNA sequencing, you get Sanger. He has given protein sequencing also, and there is Sanger's reagent, which is used in this sequencing, 1,fluoro-2,4-dinitrobenzene, and dancyl fluoride. And the second kind of sequencing method is peptide sequencing, that is given by Edman, also known as Edman's degradation. The compound used in case of this is phenyl isothiocyanate. And in order to determine the protein absorbance, they use like some dyes. Names are enough, where they use copper ions, that is cupric ion, that is in biuret method. And in Lowry's method, or also called as Poland method, they again use the cupric ion. Only in Bradford's method, they use Comasi blue. There is one more test called Ninhydrin test, which can be used to determine the amino acids and peptides in the proteins. Don't worry, for all this, we'll be giving the notes. So I'll be, for those that are just memory based, I'll be going bit fast. Otherwise, concept wise, I'll be going slow. So let's start carbohydrates. Carbohydrates are the polyhydroxyaldehydes and polyhydroxy ketones that can be hydrolyzed into the monosaccharides. Carbohydrates are also known as hydrates of carbon. These are most abundant, and monosaccharides, you know the example, when you have a single carbohydrate, you call it as monosaccharide and oligosaccharides. So coming to the properties, they'll be colorless, they'll be crystalline, they'll be soluble in water. and they'll be insoluble in nonpolar solvents. The most abundant is D-glucose. So coming to the types of functional groups, it can be aldoses and ketoses. How does aldose look? Aldose looks C double bond OH. This is aldose, CHO. How does ketose look? It looks like C double bond OR. Examples are important. You should know which is aldohexose. Glucose is a aldohexose, and glyceraldehyde is a aldose. And ketose, fructose is a ketose, like it has a ketone group, and dihydroxyacetone. Here again, can anybody tell which is the exception for the optical properties in case of amino acids? Yesterday we discussed optical properties, right? What is the exception for optical properties of amino acids? All amino acids has optical properties except which one?
Glycine.
Yes. So here also, except dihydroxyacetone, every carbohydrates has the optical properties. I think no need to explain enantiomers and optical properties again, which we have already dealt yesterday. So enantiomers are non-superimposable mirror images of each other. If you can, like, if you have CHO here and you have OH, this is an enantiomer. And again, even in case of this also, they use D and L system. This is D and this is L. In case of carbohydrates, what happens? They use the penultimate carbon as a reference. Penultimate pick the last one. We'll start the numbering from the group, aldehyde group side. So this is 1, as you can see here, 1, 2, 3, 4, 5, and 6. We'll take this as reference to say whether it's D form or it's L form. For every molecule, if you see here also, it is D-glucose, right? You have OH on right side. This is D-galactose. You have OH on right side. This is D-mannose. You have OH on right side. So they use DL system in order to say the absolute configuration of the carbohydrates. The next is epimers. So epimers are when you have two sugars and they differ in their stereochemistry at the single carbon atom. If you see here, stereochemistry is that whether the OH is present on the right side or the left side. That is the stereochemistry. So if you see here, between D-glucose and D-mannose, which is differing? Which carbon is differing? Which carbon is differing?
Second.
Yes.
Fourth.
Yeah, the second one is differing. So these two are C2 epimers. When it comes to D-glucose and D-galactose, you can see here the fourth one is differing. So these are called C4 epimers. These are example for the aldoses, aldohexoses that you can see here, and you have examples for the ketoses like sorbose, tagatose, fructose, and psychose. These carbohydrates, no, they won't stay in the cyclical form. What happens is, if you take the structure of these carbohydrates, there is a aldehyde group here, and there is a OH group here, and also here. What happens is this OH group, C double bond, this aldehyde group, C double bond OH R1, and OH group, R1OH, these two will react and it will form a cyclical form. This reaction will give you hemiacetals and hemiketals. How does this reaction happen? In this reaction, you have R1. If I take it as R2, you will have COH, CH, O, R2. You'll have something like this. So this is hemiacetal, which is formed by acetaldehyde. How is hemiketal formed? Hemiketal will be formed by C double bond O. You have R1 here and you have R here, plus you have ROH. So it will give rise to OH, R, and OR. So these carbohydrates will react in that way to give rise to the cyclic compounds. Like this. You can see here. So this cyclic compounds, if you can see here, the fifth OH is the OH attached to the fifth carbon atom is reacting with the aldehyde group to give a six-membered ring. If it reacts with the fourth carbon, it gives a five-membered ring. So carbohydrates will exist in the monosaccharides will exist in the cyclical forms in the aqueous solution. So coming to the ring structure, one more point is, in this ring structure, if you can see, this first carbon atom is called, give me a minute. Okay. Here. So in glucose, the first carbon atom, that is the aldehyde carbon atom, is called anomeric carbon. In case of fructose, the carbon that is going to react, this carbon is called the anomeric carbon. If you come and look at the structure, this is the anomeric carbon. This is the anomeric carbon in the structure. If you see here, this is the first carbon atom of the glucose that is reacting with the fifth carbon atom. It is forming a ring like this to give rise to this ring. And this is the first anomeric carbon. If the OH lies below the first anomeric carbon, it is termed as alpha glucose. That is below the plane. If it is above the plane, it is called beta glucose. Is it clear, alpha and beta glucose, or it got confused because I switched too much? Is it clear, or shall I explain again?
It's clear.
Okay, thank you.
Ma'am, repeat alpha and beta glucose.
Okay. See, you have glucose where you have C double bond O. You have glucose where you have C double bond OH, and you have some groups here. Let's take fifth carbon atom to which OH is attached. Okay. This O will react with this to form a six-membered ring. Is it clear that this is the first carbon atom is called anomeric carbon atom? Like in case of aldoses, the aldehyde group carbon atom is called the anomeric carbon atom. And in case of ketoses, the ketone group carbon is called anomeric carbon. Is that clear?
Yes,
I
ma'am.
hope it's okay. So Here, it comes here. This is the first carbon atom. If I start the numbering, I can keep the name like this. I have CH2OH here. So when we look at this first carbon atom, if the OH group is lying below the plane, it is called alpha glucose. If the OH group is coming above the plane, we'll call it as beta glucose. Is it clear now? It's just about whether it's above the OH group is above the plane or below the plane. Is it clear? Not getting response. I'm moving on. So derivatives, coming to the derivatives of the monosaccharides, this hemiacetal groups, no, these groups can react. They can react with a lot of molecules. Like if they react with OH, they will form glycosides. The example for glycoside is streptomycin. What is streptomycin? If anybody remembers what is streptomycin?
Antibiotic.
Yes. Streptomycin is a carbohydrate in which the hemiacetal is reacted with the alcohol. How does that look like? It looks like if you have a hemiacetal like this, R1, O, R2, and you have H. Let's take another one with the OH group. If you take this, you will have something like this. You have water molecule released. This is called as acetals. Hemiacetals will react with the alcohol to give acetals. I think this will be enough for you that if the hemiacetal reacts with the alcohol, you will get a acetal. If the sugars react with, like if the sugar reacts with acids, or if there is oxidation or addition of oxygen somewhere in the sugar, you are going to get the sugar acids. For example, in case of glucose, if the acid, if this group is turned into acid, if this becomes COOH, that is when the sugars are oxidized, you get the acids. Sugars are oxidized, you get acids. Let's say I'm oxidizing this particular carbon of the sugar, which means this becomes COOH. This all remains the same. Then I call it as gluconic acid or aldonic acids. In general, aldonic acid, otherwise gluconic acid. See, I'm just explaining how the sugars, I mean monosaccharides, can react with a different group and form the derivatives of monosaccharide, because in the natural system, you will get the derivatives of the monosaccharides, not just the monosaccharides as such. You get the derivatives also. That's why I'm giving examples. So, if in acids, if this group gets oxidized and becomes COOH, I call it as glucouronic acid. We'll be seeing examples later. This is glucouronic acid. If this group also gets oxidized to COOH, and this group also gets oxidized to COOH, we call it as glucaric acid. To summarize it, if in the glucose, the CH4 group is changed to COOH group, it becomes aldonic acid. If the penultimate carbon OH changes, carbon changes to COOH, it becomes glucouronic acid or alduronic acid. If both of this occurs, then it is called glucaric acid, or also known as aldaric acid. The another possibility is sugar alcohols. Where the glucose, where in sugar alcohols there happens the reduction from the glucose you get, means the OH is, I mean in the CO, the O is removed and you get a alcohol. So from the glucose you get sorbitol. It is simple. When the glucose is reduced, you get a sorbitol. When the xylose is reduced, you get a xylitol. Another possibility is you can get glucosamines. Glucosamines are amino sugars. Here, what happens is OH group of any of these structure OH group that is present anywhere, let's say this OH group, this will get replaced by NH2, or it will get replaced by acetylamine group. Acetylamine group is CCH2. So this gets replaced by NH2, or this will get replaced by acetylamine group. Acetylamine group looks something like NH, CH2, C double bond. This is also known as N-acetyl D-glucosamine. Where can we find N-acetyl D-glucosamine?
Cell wall.
Yes, bacterial cell wall. We can find it. Coming to disaccharides and the glycosidic bond. So what happens in the glycosidic bond? So in glycosidic bond, what is this atom? Is this anomeric atom or not? This is a anomeric carbon. This is alpha D glucose. I forgot to write it. This is alpha D glucose. This is beta fructose. You can see here, like here, okay, this is anomeric atom and you have OH in the below. So this is alpha. For fructose, which is the anomeric atom? Come on, this is 1. There is 1. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. For fructose, which is the anomeric atom? I got your
CH2OH.
reply. Okay, question. No, you can get simple questions like if the sugar gets replaced, I mean, sugar gets reduced, what will be the product of it? Or sugar gets oxidized, what will be the product of it? That too, I am telling in deep, you can get that. Or else, what are reducing sugars or non-reducing sugars? It's enough if you can remember the, the reducing, non-reducing sugars and the bonding. What is like alpha 1, beta 2 bonding for sucrose? That kind of questions you can expect. For questions, don't worry, we'll be giving the notes for you people with which you will be able to revise. No need to go in deep. I'm explaining because you people can't get if I give bullet points. That's why. Here, this is not the anomeric carbon. I'm talking about fructose. Fructose is a ketose. It has ketone in the second carbon. So the second carbon becomes the anomeric carbon. So what happens is the first anomeric carbon of this so what happens is the anomeric carbon of the C1 of the glucose and the C2 of the fructose will form the bond. That is a glycosidic bond here. Okay. So in case of sucrose, no. Sucrose and trehalose are the only non-reducing sugars among the disaccharides. Let me explain reducing, non-reducing, then you will get what is it. So reducing sugars are those in which anomeric carbon is free. Anomeric carbon is free. If anomeric carbon is free, they'll be able to open the ring and close the ring whenever they want. So they are free to do that. They are reducing sugars. But for non-reducing sugars, what happens? The anomeric carbon will not be free. Means it's tied up. That happens in case of sucrose. In case of sucrose, no. I'm unable to. Okay, let me write it here. In case of sucrose, what happens? No, you have in alpha glucose, you take C1. And in fructose, you take C2. These two are anomeric carbons, right? And these two are involved in bond. So sucrose doesn't have reducing ends. That's why sucrose is not a reducing sugar. Only sucrose and trehalose are exception to reducing sugars. They are non-reducing sugars. Otherwise, all monosaccharides and all disaccharides are reducing sugars. So in sucrose, the bond will be called as alpha 1 and it will be written as beta 2, glucose this side and fructose this side. You can write bond like this, alpha 1, beta 2 and the fructose. You come here, if you look at the table here, you will get an idea which one has which one. So this table is important where the sucrose, look at the bonding of sucrose, you have alpha 1 and beta 2. These two are anomeric carbons. These are involved in the bonds. So it is a non-reducing sugar. If you write lactose, it is beta 1 and beta 1 of galactose and the beta 4 of glucose. Means galactose, anomeric carbon of the galactose is involved. If you take C1 and in the glucose, the C4 is involved. You can write here. In glucose, this fourth one is involved and the reducing end is free. Even in maltose, you can see in maltose, it's alpha 1 and alpha 4. So this alpha 1 is an anomeric carbon that is involved here, but alpha 4 is not an anomeric carbon. You have anomeric carbon alpha 1 here. This is the reducing end of this sugar. This is the non-reducing end of this sugar. Is it clear or I have to explain reducing and non-reducing again? Is it clear or shall I explain reducing, non-reducing again? I want response, otherwise I can't continue. I'm not getting any response. Is it clear reducing and non-reducing sugars or shall I explain again?
Explain more.
See, reducing, we call it a reducing end. Everybody got that aldehyde one, no? That aldehyde will react with the OH group. Did you people get
Yes,
that?
ma'am.
Like how, yes. So, anomeric carbon will form the cycle. It's simple. When the anomeric carbon is free, it can open the chain and it can close the chain, right? If somebody who has the power is free, they can do anything. It is as simple as that. This anomeric carbon has the power to open the chain or to close the chain. So whichever sugars that has anomeric carbon free at one end If you can see in case of maltose, this has anomeric carbon free, right? Maltose has anomeric carbon free, right?
Yes, ma'am.
So maltose has reducing end and non-reducing end. So maltose, excuse me. So maltose has reducing and non-reducing end. Hence maltose can act as a reducing sugar. But sucrose does not have a reducing end. You see here, both the anomeric carbons are involved in the bond. So this sucrose becomes non-reducing sugar. Got the point?
Yes, ma'am.
Okay, thank you.
Yeah.
So coming to polysaccharides. Polysaccharides doesn't have sweetness. Hence, they are also called as non-sugars. So they can be of two types. They can be structural polysaccharides, which can provide the mechanical stability to the cell, or they can be storage polysaccharides, which can give the which can act as the carbohydrate source that releases the monosaccharides. In case of animals, important polysaccharide would be glycogen that acts as the storage compound. So let's see the examples for homopolysaccharides and heteropolysaccharides. Homopolysaccharides are where you have same repetitive units. If you have glucose, 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 and glucose, it is called homopolysaccharide. If you have glucose, galactose, fructose, it is called heteropolysaccharide. So in homopolysaccharide, the first example would be starch. Starch is made up of amylose and amylopectin. So amylose is alpha 1,4 linkage. Amylopectin is alpha 1,4 and alpha 1,6 linkage with the branching between every 25 to 30. For every 25 to 30 glucose residues, you will have branching. Means if you have glucose, glucose alpha 1,4, glucose alpha 1,4, glucose alpha 1,4. So you will, for every 25 to 30 residues, you will have glucose alpha 1,6. So amylopectin is a branched polymer. If it happens like this, it becomes branched. So amylopectin is a branched polymer, amylose is unbranched polymer. Iodine test is used to detect the starch because the iodine will go and it will bind in the amylose to give the blue color. Remember iodine test that is used to determine the starch, and coming to amylopectin, it will give reddish brown color. Remember the color. Pectin will give the amylopectin will give the reddish brown color. Aminos, coming to glycogen. Glycogen is the major storage carbohydrate and it is a highly branched amylopectin. In glycogen, what happens? No, for every 10 to 15 glucose residues, you can see the alpha 1,6. So it is highly branched form of amylopectin. It is found mostly in liver and muscles. These points you can read out yourself. Then coming to cellulose. Cellulose is a linear unbranched homopolysaccharide with D-glucose. Here, beta D-glucose, two beta D-glucose are there. It is a structural polysaccharide for plants and it is not hydrolyzed by the human system. It is the first most abundant organic compound. Coming to chitin, chitin is a homopolysaccharide. It is composed of N-acetyl D-glucosamine. N-acetyl D-glucosamine, as I already told, it contains amine group in it. Remember it, it contains the amine group. And it acts as a structural polysaccharide in fungi, exoskeleton of insects and crustaceans. It is the second most. So the first most abundant is cellulose. And the second most abundant would be chitin. If you look at the structure, you will get an idea. So cellulose, as I have already told, it's just like starch. Sorry, not starch. Cellulose is unbranched. What I meant by unbranched is this: cellulose is linear, where you have glucose, then glucose, then glucose. There is no branching. But if you come and see the starch, you have branching here. Here, the anomeric carbon atom is free, so it is reacting with this, and it is forming the branches. I think this is it. So reducing non-reducing sugars, I have already explained. And the glycoproteins are those carbohydrates with the proteins will be called glycoproteins. Remaining will provide in the notes, which you can refer. If any concept you haven't got, you can ask me now. I think it's too much of a chemistry for a class, right? So many structures. Yeah, it's too much of a chemistry to understand in a single class. Is it clear, or how? You can ask the question in the next class, like once you go through it, and then you can ask the question in the next class or subsequent classes. Right now, are you getting confused in any topics, reducing, non-reducing sugars or anything? Yeah, I would try. Yeah, I'll upload carbohydrates notes. I'll upload. Proteins, I think it would take a day. Okay. Was the pace okay today? Like it was too fast or slow, or how? You were able to follow, right? You people were able to follow me, right? Okay, Dipanj. Okay, Pradeep. Okay, if you have any questions, feel free to discuss in the agriadic community. I'm not seeing any questions in the agriadic community. So I'm telling again, even if you have a small doubt, you can post in the agriadic community and be active in it, and be active in the discussions also. That will help you.